Okay, so question number, to determine the bond order for F2, F2 plus, and F2 minus, which molecule should be the most stable? So to answer this question, I'm going to draw the molecular orbital diagram, and I'll do it for F2, just so that it'll be easy for us to compare what happens if it gained an electron and what happens if it lost an electron. Let's try to draw this molecular orbital diagram. So the highest in energy in terms of the orbitals for F2 would be the sigma star orbital in 2p. Below that is the pi star in 2p. And then the star signifies that these are anti-bonding orbitals. And when there is no star, these are known as bonding orbitals. So here is just regular pi orbital of 2p, and then just a regular sigma 2p orbital. And then on the left and the right sides, I can also show where these orbitals came from. So this is the 2p orbital. And then you kind of just draw dotted lines to show that these are from 2p. Okay, so now let's do the same thing, but for the 2s orbital. So below the 2p, we write 2s. So we have the anti-bonding sigma star of 2s that is higher in energy than the sigma 2s. And again, we can show where the electrons will come from, the 2s orbitals. And below that is 1s. So notice that for both 2s and 1s, there are no pi bondings that occur. And then finally, it's just the 1s bonding and anti-bonding. And then I'm going to show these on the side. So hopefully I have enough room to even like take notes for this question, but I'll try to fit it on the right side. Okay, so this is basically our skeletal structure, you can call it, of the molecular diagram of F2. So all we need to do is fill in the electrons. So if we think about F2, so I'll write it here. F2 contains $18 electrons in total. So 9 of them come from one fluorine, and then the other 9 come from the other fluorine. So if I were to fill in all of the electrons, you can think of the left and the right sides, like the 1s, 2s, and 2p, just to be like a separate fluorine atom. So if I were to fill in that orbital filling diagram, and put the electrons in, I can put the 9 from this. 1, 2, 3, 4. And our 2p should have the 3 orbitals here. Because a p orbital can hold 6 electrons. So that's why we need 3. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's from one fluorine atom. And then for the second fluorine atom, I'll do the same thing. 1, 2, 3, 4, 5, 6, 7, 8, 9. So now that I filled in both of my individual fluorine atoms, now we can see where the electrons will come in and fill up all of the sigma and sigma star and pi star orbitals in this molecular orbital diagram. So since we have 18 in total, I'm just going to fill in the electrons the same way you would with opposite spins. So 1, 2, 3, 4, 5, 6, 7, 8. So I need 18 in total for F2. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So notice that when I have 18, then it stops at the pi star orbital. And now we need to calculate the bond order. So I'll write down the equation of bond order. I think I can just fit it down here. So bond order is equal to the number of electrons in the bonding orbitals minus the number of electrons in the anti-bonding orbitals. Divided by 2. Okay, so this is the equation for bond order. Just put this in a little cloud to separate it. And now let's calculate the bond order for F2. The number of electrons in the bonding orbitals are the ones that are in all of the sigma and pi that doesn't have the star. So let's count it out. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 in the bonding, and in the anti-bonding, which is the ones with the star, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 10 minus 8 over 2, which is equal to just 1. So now let's see what happens if we were to gain an electron. So let's do this in green. If we were to gain an electron, then we would have, not gain an electron. F2 plus means we lost an electron. Because it's positively charged, we lost 1 electron. This means we now have 17 electrons in total. So it's going to look the same as our F2, except this time we lost an electron. So let's say in the green is F2 plus, and we lost an electron there. Let's try to calculate that bond order. The number of electrons we have in the bonding will still be 10. But this time, the number of electrons in the antibonding, we took out 1. So now we have 7. So 10 minus 7 divided by 2 is equal to 1.5. And with that same approach, we can find out what happens if F2 gained an electron. So now we have 19 electrons in total. And I'm just going to draw an orange electron up here. So now that we have an extra electron in the sigma star, and it'll look like this in our other two orbitals. So now let's calculate the bond order of F2 minus. So now the number of electrons in the bonding orbitals is still going to be 10. But this time in the anti-bonding, there's going to be 9. Divide that by 2, we get 0.5. Okay, so back to the actual question. We determined all the bond orders, but now we need to know which molecule is the most stable. So I'll have a little explanation here. Stability is proportional proportional to bond order. So that means the higher the bond order, the more stable the compound is. So therefore, F2 plus is the most stable. Since its bond order was the 1.5. So now let's see what the junior tutor said. Bond order is given by the number of electrons in bonding molecules minus the number of electrons in antibonding divided by 2. And they tried to write out the molecular orbital for F2. So you can see it's sigma 1s, sigma 1s star, sigma 2s, sigma star 2s, and so on. And then, so then they showed that there are so this is right. Bond order is equal to 1. For F2 plus, you can see that 1 electron was removed, and they got a bond order of 1.5. And when you gained an electron, there's now an electron in the sigma star 2s orbital, and its bond order was 0.5. So bond orders that are whole numbers are more stable than fractions. Therefore, F2 is the most stable among the 3. So I'm just going to say that the solution is correct. I can also just mention that stability can be shown as proportional to bond order, making F2 plus the most stable. But I'll still mention that this solution is correct since they did give all of the different bond orders.